Hello there. Today we'll be doing power x of n, and we'll be using the umpire method. So umpire method, to review, is to first understand, match the pattern, plan, implement, review, and to evaluate. So in understanding, we're going to list out our test cases, edge cases, and what we're going to do is predict the time complexity, time and space complexity. Then we'll match the pattern, and we'll create a plan, a couple sentences to ensure that we will get to the correct result. A diagram, a drawing. Then we'll implement it in code, and we will then review by checking our test cases and our edge cases to make sure that we are going to be all right. And lastly, we'll evaluate the time complexity. Okay, so let's get started. So we're going to list some test cases. The test case here, we have 3 given to us, and this is 10 to 2 to 10 power. This basically means 2 times 2, 10 times, and we'll get a total of 1024. Here we have 2.1 times 2 third power, which is 2.1 times 2.1 times 2.1, 3 times, and that will get us 9.26. And lastly, we have 2 to the negative 2. We will have to handle negative powers as well. So what that means is that basically we take a 1 over the amount of items that we divided. So basically 2 to the times 2, 1 over that. Alright, so those are our test cases. As some edge cases would be, like, let's suppose this is 0. We never thought about that. So 0 to 10th power is basically 0 to 10 items. And that's basically going to give us an output of basically 0. And if, suppose, on the other hand, we had a power of 0, which is likely, can occur. So we're going to return 1. That's just how powers work. Alright, so we've taken care of our edge cases, and we're going to predict the time and space complexity. So one way to do this is O of n time. And basically that is to spend all our time, 2 times 2, and then we'll have 4. And then we'll take that 4 and multiply it by 2. And then we'll have 8, and then we'll multiply that by 2, and we'll have 16, and so on and so forth. This will take O of n time. Another way to do this is to divide and conquer, and that basically means that we're going to do this in log n time. How we're going to do this in log n time is basically we're going to take these 2's here, as you can see here. These are a total of 10 2's, I think. And we're going to take all of these and multiply them together. Each pair, right? So we're going to take these pairs, this pair, this pair here, this pair here, and I'm not sure about that. There's extra 2 here. And now we have only several more operations to go. So instead of doing this 10 times, now we're doing it, we have 3 times, and now we have 4 times 256. So at each layer of our, we will be dividing it by half. Half the number of operations are needed to get our code together. So once we roll back up, we have 256, then we have 256 times 4, and now we have 1024 at the top. So when we send this back up to our top of our recursion tree. Yeah, and so what would be the space complexity? Space complexity will be the memory usage for storing the recursion calls. So basically there'll be 4 recursion calls here, and essentially this basically means this is the last one, returns 1, but because it's at power 0, but we need to store this in memory. It's not free. Like recursion is not free. So it's going to be O of log n space to use recursion, as this needs to be in the memory stack, and we need to store this. Okay, so space, and this is time. All right, with that, we already matched our pattern, which is divide and conquer, as that is the better of the 2 ways to solve this problem. And here's our plan. We will multiply the number by the number and divide the power by floor 2. So this basically means that every time we go through this layer of recursion, we're going to have half the number of items to multiply, and we're going to floor it by 2. Every time that it's odd, we will multiply the results by the number. That way, we can restore that number for later, because we know for sure we will be taking this particular result from the multiplication that we get at each particular layer. We'll be squaring basically the number that's available to us, and this means that we will be at points in time we will have odd powers, and we can't multiply that in. So we'll multiply it in at our particular level, right? So like when we move from like let's say 16 times 16, which is 256 here. Basically this becomes 256 as you can see here, and of course now this becomes 256, and we multiply that by 4, and we get 1024, and we go to the top, and that way we can return 1024, right? So that's what we're gonna do. That's the plan, and we will do this by recursion. So let's implement it. It's not too hard. So let's create a recursion, and we will take the number and the power, and we'll return an int. All right. So if the number is equal to 0, return 0. If the power is equal to 0, return 1. Otherwise, what we're going to do is set the result to be equal to the recursive call of number times the number. And this way we can reduce our exponents by half. So power is going to be divided by 2. Now, at the end, what we're going to do is return our result and times number if the power modulus 2 is equal to 1, which is odd, and otherwise we're just going to return the result. With that, we can return our recursion of this particular number, which is x, and our particular power, which is n, and we will get our answer. Oh, this is supposed to be a float, isn't it? Okay, very well. Yeah, and that's it. Let's review to see if that is the way that the code will work. We do not have space for that, so let's move this code up. And yeah, so let's try to take this example 222, and let's see if we can get our answer, or we should test our edge cases. But either way, we're going to test some of these and not the other ones. So we take the 2's. We have 2 to the 10th power. So it does not hit any of these base cases, and we now have 4 times to the 5th power. So we have 4 to the 5th power recursion in our stack. So our stack had recursion of 2 to 10th power. Now we go to the next layer of recursion, and we have basically 4 times 4 is 16, and we have 2 in our recursive stack. Now, lastly, we're going to have recursion of 256 and 1 in our power. And lastly, we're going to have a recursion of like 256 times 256. I need a calculator for that. I'm not sure what that is. So it's going to be 0 power. And that's going to return us a 1. So basically, it's going to be 1 times the number, which is 256. And this is going to return 256. Now, this is going to be 256 times, that's our result, as you can see, this is what's returned. And we're going to multiply this by nothing, because this is going to be 0, so we're going to straight up return 256. And now, here, because this is odd, we're going to have 256 times our current number, which is 4, and we're going to return 1024. And this is going to return 1024, and we have our result. Suppose that we had a power of 0. Well, straight up, we're just going to return 1. And if I had a number of 0, we'll straight up return 0. And that's all. So with that, I'm pretty sure that this code works, and we're going to evaluate the runtime. And it looks like the runtime is log n, because this is 2 to the log of 10 n, which is going to be like 4, 5, somewhere around there. So essentially, it's going to be much faster. So with that evaluation, we have a log of n, and space complexity, as you can see, the recursion is a log of n space. How we're doing on time? We're doing pretty good. So let's just run the code at this point. Oh shoot, we can't run the code because there are way too many comments in the way. So let's just comment those out, and we can run it now. As you can see, this code is accepted, and let's submit. Oh wait, that we can't do that, because we do need to do something. So absolute value of n, we forgot to test our test case of -2, and so what happens is that our result is we did not test our test case of -2. So if return 1 over results, if well, if our number is less than 0, else result. So basically, if it is less than 2, we have to do a 1 over, and let's test that test case as well right now. So a -2. The reason why we did not catch that case is because we did not test it, and that happens sometimes when we start things off too quickly. But we solved it this time around, and let's pull this code to the top of our implementation, and so it's a little bit cleaner. So as you can see here, what we did was create a recursion code, and lastly, we made sure to take care of that edge case of negative numbers, and so we could return the proper item. So let's submit it one more time. And it was very fast. So with that, we have solved this problem. If you enjoyed this video, like and subscribe. If you want more videos like this, yeah, just comment below, and I'll see you in the next one. Thank you. Bye.